All right, this is for calculus on the unit on infinite series in the second part, and we're talking about one more name series, the binomial series, and then the way we can use lists of predefined power series to evaluate power series for more complicated functions. All right, first, the binomial series. This is another named series like the geometric series. If we have a function that's representing well, we're trying to come up with a series that represents a function of this form, 1 plus x to the k power where k is any constant, then the series is called a binomial series. And it's simply because this is the form for a binomial. Um, we talked about the binomial expansion, right? If you're trying to have some a plus b to the third power, you can use the binomial theorem to be able to expand that. So it's just named that because it's the same form. Let's analyze it really quickly. I'm not going to do as much writing in this video because we're just going over and over the same procedures. A couple of things I'll show you where it gets more complicated. So let's say we wanted to find a Maclaurin series, so centered at zero, at c equals 0, or x is equal to 0 for this general binomial series, 1 plus x to a k power. Then we could take our derivatives of the function. We could plug in the centering value here and get these values. And then the first term, the pattern would be, we want to take the function at the centering value plus the derivative of the function at the centering value times x minus c plus the second derivative over second factorial for the x squared term, and so on. You would plug in 1 for the first term here. The coefficient would be k, whichever this k that's provided here is in the original problem, times the x, which would be x minus 0, so x. And then there would be k times k minus 1 over the 2 factorial, and then k times k minus 1 times k minus 2 over 3 factorial, the x cubed term, and so on. So it's not easy to write this in a general form because you just continue to have more and more k minus 3, k minus 4, k minus 4, 5s on there. But you can see that there's definitely a pattern here. And if you do ratio test or something similar, you can show that this has an interval of convergence from -1 to 1. So this is called the binomial series. It's good to recognize it, that's that form. Okay, but what if we want more complicated functions, like especially if we have compositions of functions, like the function f of x is sine of x squared, so there's an x squared function in sine of an x. Okay, if you take the first derivative, you would get the outside derivative is cosine of x squared, but then times the derivative of the inside, which is 2x. The second derivative would now require product rule, so first times derivative of the second plus second times derivative of the first. And you can see how these derivatives would get out of hand very quickly and get super complicated. Right, so while it's possible to do that, it would be very difficult to write anything other than a second or third degree Taylor polynomial for this, and definitely difficult to come up with a general expression for the Taylor series. But in cases like this, we can employ a pre-calculated list of standard power series for certain elementary functions. And this would be a list of such functions. You're going to be allowed to, we're going to give you a list like this in class, and you're allowed to use the list on this unit test that's coming up. But you, of course, do not have availability of this list for the AP exam. So we do strongly recommend, and College Board recommends, that you memorize 3 of these. So each of these is at a predefined centering value and has a known interval of convergence. So 1 over x is easily represented by this power series that happens to be centered at 1. 1 over 1 plus x is centered at 0. Natural log of x has this structure that's centered at 1. And then e to the x, sine of x, cosine of x have specific terms here centered at 0. Arctangent we're given on the form, arcsine, and then the binomial one that we just derived. Okay. These particular ones, e to the x and sine x and cosine of x, are all powers of x, straight power series with centered at 0. So I'm going to show you how I remember these forms. And then if I need to come up with this, I try to figure it out from writing out the terms. So on the list, you've got some terms written out. But you also have an expression for the nth term, which is handy if you're trying to write them in summation formation or forms, right? All right, so let me show you how I memorize these. I memorize e to the x. It's simply 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5 over 5 factorial, and so on, right? So it's really the most straightforward one, right? E to the x simply has every term with a constant, an x term, an x squared term, and the factorial on the bottom matches the degree. So it's perfect to that. And that's actually pretty easy to find this. So that's x to the nth power over n factorial. It's not alternating, so the sum form of this is n equals 0 to infinity of x to the n over n factorial. So that's easy to memorize. I memorized the cosine and the sine from that one. So if you look at the cosine and the sine, they each include half the terms. So the sine doesn't include this term, but it includes the x term, the x cubed term, the x to the 5th term, the x to the 7th. So it includes all the odd powers, and it's an alternating series. And the cosine one includes all the even powers, x squared, x to the 4th, and so on, including the constant term, which could be considered x to the 0, which is also an even power, right? So the way I remember it is this. Cosine and sine, c comes before s. So this is going to be c first, then s. And that means that the cosine one is the one, cosine of x, that is represented by 1 and then all the even terms. So an x squared over 2 factorial, x to the 4th over 4 factorial, x to the 6th over 6 factorial, and so on, except it's an alternating series starting with the positive one. So 1 minus plus minus. Let's make sure that's right. The cosine one is the one that starts with the 1, alternates, and has the even powers. And then the sine is the one that starts with the x and includes the odd powers from the e series. So x cubed over 3 factorial, x to the 5th over 5 factorial, x to the 7th over 7 factorial, and so on. And this is an alternating series as well, okay? Plus. All right, if I had to write them in summation form, I would figure those out on the fly from this. N equals 0 to infinity. It's an alternating series, right? And if this is now you have to think of this as the n equals 0 term, right? Usually we write that way, right? So that this becomes, let's see, if this starts with positive, this is an n here. And then if this is n equals 0, this is n is 1, this is n is 2, n is 3. That means this is always twice this. So this is going to be x to the 2n, and then over that same number, 2n factorial, right? So this is the structure for cosine. Let's see if we got that right. Cosine has negative 1 to the n, x to the 2n over 2n factorial, exactly. And then for the sine, n equals 0 to infinity, negative 1. But we want this to, let's see, again, start at n, right? So that starts out that, but this is going to be x to the 2n plus 1. So 2n plus 1, and this is 2n plus 1 factorial. Yep, and that should match the general term for this as well. So that's how I memorize them. I memorize this one, and then I know that each of these are half of those terms. And I start with cosine before sine, so this starts with the cosine one and alternates, and this starts with the sine one, starts with this term and alternates. And you got to remember that they're alternating series, starting with positive and then negative, positive, negative. All right, so that's how I memorize them. I would recommend strongly that you memorize those three. You're definitely going to need those somewhere on the AP exam. All right, so let's show you how you can use such a series. So let's say that you want to find a power series for f of x is cosine of square root of x. So what you do is you start by writing out the general one, which is cosine of x is 1 minus x squared over 2 factorial plus x to the 4th, and so on, or this is its general term. And so then that means that the cosine of the square root of x means you just simply replace all the x's with the square root. So this is 1 minus the square root of x squared over 2 factorial plus the square root of x to the 4th over 4 factorial minus square root of x to the 6th factorial, and so on. Or you could write this as, you could say f of x is equal to the sum of n equals 0 to infinity, and jump up and use the general term, negative 1 to the n, but when you write that x, write it as the square root of x being raised to the 2n over 2n factorial. Okay, simple as that. There are properties that back this up that say that if you have a power series of a function of x, you can find the power series and then apply the function to the x. All right, so kind of nice. If you had, let's see, things that are multiplied, like your function f of x is an e to the x times an arctangent of x, you could write out the standard power list, from the list power series for e to the x, the one for arctangent, and then if these are multiplied, you have to imagine you're taking an infinite number of terms here and multiplying by an infinite number of terms here. So it's not just the like this one term times this x. You have to then do like distribution. So it means this entire thing here times 1 first, right? And then this entire thing over again times x, plus this entire thing times x squared over 2 factorial. Then you would want to distribute all these terms, right? So you just write out like 3 or 4 of them, right? And then you get this big long thing, and then you have to combine like terms. So the lowest order thing here is an x, so that would go first. Then there's an x squared, right? So that would be next. And then for the x cubed, there's one here and there's one here. So then you have to combine that. That means we have a negative 1/3 plus a 1/2, which combines into positive 1/6 x cubed. And then for the x to the 4th, there's an x to the 4th here. There's an x to the 4th here, and there's an x to the 4th here. So you have to write out enough terms to where you can get all the beginning ones, right? And so if you take that this is, let's see, x to this is a negative 1/4 or negative 1/3 x to the 4th here. There's a positive 1 to the 6th there, and a negative 1/18th, and that's what the x to the 4ths are. Those do combine to the fraction negative 2/9, right? So it's a lot of work if you want to write this. And here's the thing. If a question asks you to find a power series, you're not allowed to leave it in this form because this form is not in a power series. A power series has individual terms that are each x to a power. So you do have to do this, this combination. Now, do you have to write out the entire thing? Maybe after the x to the 4th, you could just go plus dot dot dot, and that would be sufficient. All right, but you can do things like this. You can take entire series and multiply by another entire series in order to get the equivalent power series. What if we had this? What if we had tangent of x? So tangent of x is not on the power series list, but sine and cosine are. We could get the sine function and the cosine function, and then you could write out a power series for the sine and then divide that by the power series by the cosine. So how can you divide a polynomial by a polynomial? By using polynomial division. So you could take the sine function and put it in here, and then divide by the cosine function, which means you carefully say, what does 1 have to multiply to get to an x? That's an x, and write that here. Multiply this by this and write it down here. Subtract, that cancels. Then you get, okay, to turn a 1 into a 1/3 x cubed, I have to multiply by 1/3 x cubed. So I put that up here, multiply and subtract. And then you'll get as many terms as you want to carry out over here. This tangent of x is equal to the result. Right, so you can do arithmetic operations on series where you plug series in for their corresponding functions. That's the point of this lesson. Okay, what if we wanted to find the power series for sine squared? Okay, well, you could, a couple ways to do it. You could find the sine function, right, which was the one that started with the x. So x minus 1/3 x cubed plus 1 over x factorial. Did I write that wrong before? I think I did. No, that's right. I had the factorials. Okay. Yeah, so you could write this out, 1/5 x to the 5th minus 1/7 x to the 7th, and then multiply by another copy. That's one way to do it. So you could do this. This is plus plus plus. 5 factorial x to the 5th minus 1/7 factorial x to the 7th, and multiply it out. That's one way. Or you can use trig identities. So you could do something like this. Sine squared is equal to 1 minus cosine of 2x over 2, which is 1/2 minus 1/2 cosine. And then just replace this one thing with a cosine, except with all the x's replaced with 2 x's. So it's 1/2 minus 1/2 times the generic term for cosine with a 2x plugged in there, 2x in that location right there. Right, so there's sometimes multiple ways to represent these power series. Okay, this I think is the last example, so let's take a look at this. Could I use a power series to approximate a definite integral? We definitely can do that. And what we're going to do is, well, let's build up to this. So first, what's e to the x? From the table or from our memorization, we know it's 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and that keeps going on forever, right? And then we could replace all the x's with negative x squareds, right? So if this is e to the negative x squared, it means we would have 1 plus negative x squared plus negative x squared squared over 2 factorial plus negative x squared cubed over 3 factorial plus negative x squared to the 4th power over 4 factorial, and so on. Okay, I'm going to simplify that a little bit here. So that is equal to 1 minus x squared. Let's see, this is 1 over 2 factorial, which is 1/2. And then that's, let's see, a negative squared. So that's going to be positive, right? And that's going to be x squared squared, which is x to the 4th, right? Then we've got, let's see, 3 negatives multiplied together is a negative. And 3 factorial is 3 times 2 times 1 is 1/6, x to the 6th. This is, let's see, 4 negatives multiplied is a positive. That's going to be positive 6 times 4 is 24, but that's x to the 8th, and that continues. And so that means that if I want to take the integral of, I'm not going to put the bounds just yet. This is e to the negative x squared dx. Well, I guess I could put the bounds. All right, that's going to be the integral from 0 to 1 of, I'm just going to replace this expression with its power series. Minus 1 over 6 x to the 6th plus 1 over 24 x to the 8th, and so on dx. And then I can go ahead and term by term apply the antiderivative. So the antiderivative of x, or 1 is x. This antiderivative is 1/3 x cubed. This would be plus 1/8. Wait, we're doing antiderivative, so divide by, that's 5, so that'd be 1, 2 times 5 is 10th, 1/10 x to the 5th, right? 10th x to the 5th, yep. Minus 1, 6 times 7 would be 42 x to the 7th, right? Yep, then plus 1, 24 times 9, that turns out to be 1 over 216 x to the 9th, and so on. And then that is what we would evaluate from 0 to 1. So you would take your 2 copies and you'd be plugging in, let's see, you'd be plugging in a 1 in this copy. So this is 1 minus 1/3 times 1 cubed plus 1/10 times 1 to the 5th minus 1/42 times 1 to the 7th plus 1 over 216 times 1 to the 9th, and so on. And then subtracting a 0 plugged everywhere. So that's 0 minus 0 plus 0 minus 0 plus 0, right? So it's just whatever this evaluates to. So you can even do things like that. You can replace a function with its power series in an integral, and then do the integral of each term of the power series. So a very flexible concept. All right. Now, of course, this is not going to be the exact answer unless you include all the terms, but you can get very close to the correct answer. And one of the last video in this series is going to be about that. If we truncate an infinite series, how much error are we dealing with there? All right, so this concludes that video on that. Should give you enough to be able to try the homework problems.